Okay, today we'll be talking about Boolean proofs. So let's take a look at a very quick overview of the whole journey that we talked about in the past 2 weeks. First of all, we are here. We started from a very simple Schnorr protocol. Schnorr protocol. Okay, here we introduce, the Peterson commitment here. Peterson commitment here, and then we got the extended version of Schnorr protocol. With perfect zero knowledge proof. Zero perfect ZK, so that we have perfect zero knowledge property to perfectly hide the private key of the prover. And then we learned the 2 techniques that to extend the Schnorr protocol even further with 2 directions. And the first is that we can commit to a vector instead of just one single value, vectorization, to prove a vector instead of just one value. Another technique, going to a different direction, that we can batch proving, saying that if we have multiple commitments, to prove the knowledge of the multiple commitments, then we can batch them together, using just one protocol instead of multiple protocols to prove the problem knowledge. So here, we just emphasize on the proof of knowledge. Proof of knowledge. Proof of knowledge. The proof of knowledge means that what we want to prove is that actually the prover has some knowledge, either one single value or a vector or multiple vector. If we combine them together, we can get a new protocol, which is we can prove, for example, a knowledge of a big file, that the big file was chunked into pieces. Then we can prove, just piece after piece, and then batch them together to prove it in one protocol. That the prover has quite a large data file. And then here is a protocol. I don't know the name. Just is some protocol. Some protocol without name. And then we go up. We can prove that one single multiplication and a single addition. That for example, we have 2 commitments, that A, B, then A. There's the A inside the commitment, and we have also a B. 2 witnesses in the 2 commitments. Then we can prove that A times B equals to some C, or A plus B times some C prime. So here we prove the prover has some knowledge that already been put into boxes, but still additionally we can still prove even the verifier cannot see the values of witnesses inside the boxes. The prover can also prove the values, they satisfy some conditions. For example, addition and multiplication. As I mentioned before, so addition and multiplication, they mean a lot, because any limited computation, bounded computation. So it's not infinite computation. Any bounded computation can be expressed as a bunch of multiplication and additions. So now we have the power that, okay, we can build a proof system for circuit satisfiability. Am I right? Ability. Correct me, yeah? Good. So now we can prove the circuit satisfiability to, now we can prove that the circuit is correct or not. Whether the prover that I don't trust that, has the proof that, okay, the computation is correct. So by using circuit. But here, the proof system is kind of quite inefficient because we have to commit everywhere of the circuit and prove each gate. That means the proof kind of will be larger, strictly larger than the circuit, the size of circuit. So that means that the proving system kind of useless because the communication cost is too high. Then we're trying to learn that, okay, how we can prove that an inner product in an efficient way. Inner product in an efficient way. Saying that, okay, the prover has a vector A and B, so to prove that, okay, the inner product of two vectors A and B, if it is equal to C, for some C. Okay. And then we can reduce that the circuit satisfiability problem into a bunch of inner product arguments. So make sure that, okay, we can somehow figure out some way to prove circuit satisfiability in slightly more efficient way. But it's not enough, okay, because it's not enough space here. Okay, that's here, okay. Now, I think last week we talked about a protocol kind of reduction of what? Okay, just reduction of knowledge. Okay, so reduction of knowledge is saying that, okay, we inspect that the proof size came from the last step of a sigma protocol. Saying that, okay, as the last step, the prover has to send a Z vector. The vector is the same size with the circuit, with knowledge. So actually, we can use some tricks to reduce the last step, the encrypted values, the Z vector, into half by using additional challenge number from the verifier. Then luckily you can do that recursively. So we ask more challenge numbers from a verifier. We actually, so it means that we introduce more interactions instead of send more values. So we get more interactions than the last values sent by prover. So eventually we can compress the proof into logarithmic size. Okay, this is a trick about proof of knowledge. Then today we're going to say, okay, we can use that trick to prove the inner product. It's a recursive inner product argument, aka bulletproof. Bulletproof. Okay, it's not end. It's not end of the story. But I think it's suppose it's the end of our first part of my session. Okay, we got a really complicated protocol here. But I think we can still optimize, do more work to optimize this protocol. I think in the next part of my session, kind of we'll introduce more stuff like KZG10. The story that we can, because here we use the Peterson increment, we use the G vector, like G0, G1, G2, Gn-1, for example, as the CRS or reference string, or can see them as the parameters to Peterson increment. They are the randomly chosen. Why they should be randomly chosen? Just because we have to make the protocol secure. Otherwise, the prover can cheat verifier. The protocol will be be broken. The idea from KZG10 will actually use different G vector, the parameters to the Peterson increment. The G vector kind of we use some specific or prepared element as the parameter of Peterson increment instead of just randomly chosen. So put like this. Like this. So it has a name like powers of tau. Tau Z. I don't understand. I don't know. No plural here. Okay, if we put more tricky stuff into the parameter of Peterson increment, then suddenly we'll have more power to make the protocol more efficient. And then we will go up. We're using KZG10 instead of Peterson increment to prove that the inner product. Again, inner product. And like hard-mod product. And then blah, 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 blah. And then we can build modern ZK system plan. Okay. Now we are here. But the good news is that, okay, I think from this part, the kind of it'll be easier. Okay, easier, not too much techniques. But here today we'll talk about this one, recursive inner product argument. And actually we're using a lot of techniques that we talked about before to make sure everyone can follow, because somebody is a newcomer. So let me quickly review that from the very beginning, that how the protocol evolved. Okay, this is just a picture for you. I think kind of give you more confidence about the follow me, go up to the top of the mountain. Okay, it's not so tough. Okay, trust me. Okay, okay, just leave it here. Now okay. Yeah. So reason why from here life will be easier. Why? Okay. Some reason here. Some reason. Okay. Before the KZG10. Okay. I think kind of before 2017. Okay, making a constructing a ZK kind of complicated, because it is complicated. we have to do a lot of techniques. We have to very familiar with the different subtlety and features of different techniques to make sure that okay, this one, that one are compatible, and that one and this one not compatible. Kind of a lot of experiences required. But after 2017, a lot of people started to realize that okay, we don't have to make things too complex. Actually, we invented a new word, kind of polynomial commitment, reinvented, I can say, polynomial commitment. It's a huge breakthrough, because when we introduce the polynomial commitments, actually we decompose the task of building a huge modern ZK system into two parts. The first part is that how can we efficiently prove a polynomial evaluation, and the rest of the modern ZK proving system is that okay, how can we use the polynomial commitment to efficiently prove the inner product, Hardy-Mark product, and other, for example, the grand product, sub-protocols. Okay, then I think, I think the people working on the protocol part can see the polynomial commitments as black box, just use it, And the people are working on the polynomial commitments, trying to push the boundary, push the frontier, and make sure that okay, this part works faster and faster. And there are a lot of innovations, a lot of breakthroughs happened in the past 4 or 5 years on polynomial commitments. So the lab here will be easier. Okay, trust me. Today's topic kind of not so easy, boring. Let's quickly go through the first, the protocol, Schnorr protocol. Okay, Schnorr protocol is that okay, the prover, we have two parties, prover and the verifier. The prover has a secret, small a, secret. And the verifier has a commitment of this secret value. We use the capital A as the commitment. This. It's a commitment. Commitment of A. So let me write down the definition, exact definition here. A equals to, okay, I have multiple definitions. The definition that I love is this. We use a square bracket to put A inside. It's the abstract definition. But abstract definition kind of very useful. We, we think about, had a higher level to think about the interaction between prover and verifier, without expanding the other definition to the bottom. Make it lab easier. But actually, yeah, the capital A has its concrete definition. So the A have one concrete definition then like this, G to A. So here we use the multiplicative group. And or A equals to A, we use the elliptic curve. A times a G. And here G is in some group, and it's a group over a elliptic curve. Okay, EC stands for elliptic curve. So I don't know how to spell it. Sorry. Yes, the protocol goes this way. Okay, first step, the prover will generate a vector, sorry, a randomness, and a commit to the randomness, and send the commitment of the randomness, and then get the challenge C. So this first step. The third step of prover is that to calculate a Z equals to R plus C. Sorry, can I use E? E times A to send the Z. Okay, I should use black symbol to represent commitments. Okay, to A, R, so all the symbols in blue are values from some field of values, and the black one are the commitments of some values. Okay. And then the verifier will verify these three elements by using commitments. So the verifier will commit Z to test if Z equals to R plus E times A. Here, I should emphasize that, okay, from now on, we're using this kind of a notation, okay, over a elliptic curve instead of this one. Why? Because in KCG10, we'll introduce more operations on groups, like pairing. So from now on, we have to get used to this notation. So for this notation, we will have such following operation that if we have G1 from group G and G2 from group G, then G1 plus G2 also in G, group G. Okay, this satisfies the group law, the invalids talk, this morning. And we also have another operation called scalar multiplication. Okay, this is addition operation. And if we have some G1 from group G and a value, for example, C from the field, then C times G1 is in G, group G. This is called scalar multiplication. So for any group element, we have two main operations. One is addition, the other is scalar multiplication. Okay, no multiplication here. Please keep it in mind. No multiplication operation over group elements. Okay. I have only addition and scalar multiplication. And the scalar multiplication actually is also the addition. Why? Because, for example, I'll have this one, 2G1 element is equal to G1 plus G1, right? And the C times G1 equals to G1 plus G1 plus G1, we have C number of G1 elements. So segment multiplication is also addition. So, but here is kind of it's a macro. You can think of it as a macro. Okay. The first step of the Schnorr protocol is commit, and the second is challenge. Challenge. And third, we'll give a name, name it open. Open. Okay, what does that mean? Open. So open, okay, this word came from, so I should talk more about what commitment is. So commitment. That's the section 0. Commitment. Commitment has two operations. First is commit a value. We got a commitment A. And also we can open A with commitment into true or false Okay. So commitment is a cryptographic primitive. Like we have to commit something, for example, on chain, and after a while, I just like I submit a small a as the kind of a review of that secret. So commit and review kind of a very common used protocol on chain for example, voting or lottery, something like that. So commitment kind of we commit something. In order to, we should review that in the future. So commitment kind of you can see it has a black box. So we put something in the box and lock it down, and then after a while, just open the box to show okay the value. Okay, it sounds useless, but it's very very useful in many cryptographic protocols. Like so to keep in mind that okay we are two different operations for commitment, typical commitment scheme, commit and open. So take a look at the Schnorr protocol. The third step is called open. But this open is not directly open. So if the prover directly opens A, then the private key will be leaked, right? If A is so secret as your private key of your wallet, kind of okay, we can do that, cannot do that, okay. But open it as this encrypted data. So Z, we can see it as the encryption of secret. Encrypted secret, okay. And thanks to the property, one very important property of commitment here is the verifier can construct the commitment of the encrypted secret by himself. So saying that, okay, the R plus E times A, so A is the public input of protocol. Even the verifier already got the A before the protocol begins. And R sent by prover as the first step of the protocol. Okay, the R plus E times A is the commitment of the encrypted secret. Okay. R plus E times A is, here's the magic because the prover can do addition to RNA. So the box, it actually is not a real box. It's a box can be added together. So that's what we call the commitment is called additive homomorphic. It's a jargon. It's a jargon from cryptography. Homomorphic. Yeah, it's an additive. Additive homomorphic commitment. Okay, what is homomorphic? Homomorphic actually is a math jargon, saying that okay, if for any phi is a homomorphic function, that we can have this equation, and phi a plus phi b equals to phi a plus b. Okay, this is a homomorphic. Okay, homomorphism. Okay, homomorphism gave us some power that even the verifier cannot see the secret, but the verifier can construct the commitment of secret, the commitment of encrypted secret. And then at the third step, the verifier asks prover to open a value of encrypted secret instead of a plain secret, unprotected secret. Now then the task of verifier easy to verify. So the verifier puts the Z into a commitment and then check the commitment. Okay, the actual meaning of the third step is check the commitment. Okay, this is all Schnorr protocol about. Okay. Okay, the protocol is easier. Okay, it's easy to understand. So if time is okay, then stop here for 2 minutes. Okay. For two or 3 minutes to make sure, okay, everything is fine. Fine. Well, nothing. Okay? Okay? Okay, good. Okay, let me stop here for 3 minutes.
So
okay.
In real world, what's group used by Schnorr protocol?
Okay, I think K1, P1. I think a Bitcoin kind of a ZKP 256 on K1. I'm not sure about that.
Yes.
Okay, yes. I mean, Bitcoin taproot in the taproot upgrade. I'm not sure about that. Which little curve does Bitcoin use? I'm not sure about that. But Schnorr code, I think a couple years ago, Schnorr protocol was protected by pattern. Sorry, patents, right? And that's why we generally will use ECDSA instead of Schnorr protocol. Schnorr protocol kind of a more complex, more flexible. Yeah. Okay. Schnorr protocol is a identification protocol, but we can easily transfer it into signature protocol. Yeah, I talked about Schnorr signature protocol instead of this one. Okay, everything's fine.
Z should be a commitment here.
Oh, Z is not a commitment. It's values. A is not a commitment. So I use black symbol to represent R1. Okay. R A. Okay, here A. Here A. Okay. Okay. Yeah.
just said capital Z. I think just
Capital Z?
Yeah.
The plural can cheat. Right. Okay, probably as a homework. You can write Z as it's not open. So that means in the whole protocol, the prover doesn't have to open anything. That means the prover can do anything. Yeah. So put arbitrary trap, the trash value into the box to fool that verifier. So yeah, you can try it. Okay, everything's fine.
Yes.
Fine. Okay, good. Okay, then let's do some more complicated protocol. So I remove this part. Okay. Okay, the second protocol is a minimal polynomial commitment. Kind of here. This protocol is here. Just the rest before the reduction of knowledge technique. A minimal polynomial commitment. So also have a prover and a verifier. Sorry. The prover wants to prove that for some fx polynomial as a secret, that's like fx equals to a0 plus a1 times x plus a2 square an minus 1 x n minus 1. Okay, it's a secret. It's secret. And then the prover committed to this polynomial by putting all the efficients into a box commitment. So we have the commitments of the put f into box is equal to a0 a1 to an minus 1, or we're using a short notation like this one. Okay, a with the arrow above a. Okay, it's kind of I'll put this stuff instead of blah blah into a commitment. Oh, sorry, I should not use this. Sorry. Then use the a equals to a1 and minus 1, or using this short notation. Okay, here I give the definition here that a0, a1 to n minus 1 equals to a0 times g0 plus a1 times g1 plus an minus 1 times gn minus 1, where the g0, g1, g2, gn minus 1, they are randomly chosen elements from group. Oh, here's the definition. We'll put the values into a box, into the commitment, and plus them together. Because this elements, we call it base element. Base element. are randomly chosen by some trusted person, an angel. Okay, angel. Okay, we have to trust the angel. Okay. Okay, the parameters are generated before the protocol begins. Okay, and the parameter can be reused again and again. If this element was randomly chosen by angel instead of prover, okay, prover cannot choose that. Okay, it's not secure. Okay. The protocol, okay, let me write down the protocol. The first step, the prover will generate a R equals to small r, and the small r a randomness. So R a vector with similarance with the coefficients to protect efficiency. Or you can see R as a encrypted key, the one-time encrypting key, and with similarance with the message that we want to protect. So R, generate R, and the prover commit to R, the R vector, and put it into the box as a commitment and send the commitment. And the second step is E. Okay. Here is not enough because the prover does not only to prove the knowledge that the prover knows some polynomial, but also prove that okay, this polynomial will evaluate at alpha, kind of equal, we got an evaluation result that is equal to some other public value. Let me write down here. So this protocol is a little bit complicated than this one, but it's okay. If alpha equals to some y, okay. So f alpha equals to y is the statement that the prover wants to prove. F alpha equals to y. So in order to this, okay, an evaluation of a polynomial can be decomposed into multiple addition and multiple multiplication, right? So, so in the map I drew before, that we can say, okay, we can prove the single addition and the single multiplication, and then we can use that techniques to combine those techniques in order to prove that, okay, this composed addition and multiplication as the evaluation that equals to some y as the public input. It's a public input, okay. And then the prover should commit more things in order to prove the. We have to, the prover have to construct another commitment like this, like this. Okay, so now I introduce another notation, a weird notation. Okay, it's an angle bracket. So I put a definition here. So what angle bracket is, that looks like this. For example, A1, A2, blah blah, A minus 1. It's a vector, and we do an inner product over this vector and another, named B0, B1, B2, Bn minus 1. So definition is, so definition of this notation is A1 times, sorry, A0 times B0 plus A1 times B1 plus A2 plus B2 plus AN minus 1 times BN minus 1. Okay, we call it the inner product. Okay, it's called inner product or dot product. Okay, the same thing. Inner product. It's inner product. Why we should care about the inner product? Just because the F alpha is indeed an inner product. So F alpha equals to A0 plus A1 times alpha plus A2 alpha square, right? AN minus 1 times alpha 2 n minus 1 is equals to a vector with a alpha vector, where the alpha vector equals to 1 alpha square alpha n minus 1 2 n minus 1. Okay. So the evaluation of a polynomial is indeed an inner product. So for the second protocol, that the goal of the protocol is how to prove the polynomial commune, saying that how to prove that a polynomial evaluation at some point that's selected by the verifier. For example, assume that the selected point is alpha. Then the prover proves the inner product. Proof F alpha equals Y. Actually, the proof proves that this inner product equals to Y. Okay. So yeah, give it a name, minimal polynomial commune argument. Actually, we can also call it inner product argument. So almost the same. Okay. And then this first step of prover, and then third step prover. So the at the third step, the prover will open an encrypted data, encrypt A, to the verifier, in order to that the verifier, such that the verifier can get enough ingredients to compose them together to get a new equipment, and that matches the encrypted data sent by the prover. So the data kind of like this: Z vector equals to R vector plus E times A vector, and send the Z vector here. The verifier will check two equations. First, check if prover has the knowledge of A. So much similar to this protocol. Okay. So the first equation, the verifier verifies that like this, puts the Z into a commitment, and verify, okay, if Z equals to R, sorry, I use black. R and A. Plus E times A. Okay. Okay, it's not enough, because this equation only guarantees that, okay, the prover has the polynomial. Okay, the verifier has to check another equation to make sure, okay, F evaluated at alpha equals to Y. Check it like this. The put the inner product of z and alpha vector. Here's the alpha vector definition. Okay, it's angle bracket, and if equals to. Okay. The right-hand side of the equation is the components from prover and verifier. We just compose them together to form a new commitment. It's like, okay, E plus E times Y. Okay. Okay, that's the particle. Okay, it's fairly easy. Okay, fairly simple. Okay, this simple particle can prove a polynomial commitment. Okay, so I stop here for 5 minutes. Then we'll show the last particle, bulletproof. So the disadvantage of this proof, the cons of this proof, that this particle is that the whole proof size is the majority part of this particle is the z vector, because z vector is in the simulance with A. For example, if the polynomial is 1 million degree, kind of in 1 million degree, so z vector will be 1 million field long. Makes the proof kind of a linear proof. It's not a succinct proof that we want. We will use the bulletproof tool to reduce the size of the third step. And then in a recursive way to compress the third step. Okay. Yeah, here we will bulletproof. Eventually, we got here. Eventually, yeah. Okay. Bulletproof IPA is a polynomial commitment. Okay. So I just stop here for 5 minutes. Okay, running right here. Oh. Okay, and here. Okay, this is for proof of knowledge. And this equation is for polynomial evaluation. Polynomial evaluation. Okay, 2 checks. Okay, any question? So. Hello, did you check the completeness? Really? Okay, good, good. Okay.
I want to ask that what does the R mean in the
R?
vector?
Here?
Yeah,
R?
vector.
R is okay. R is for the commitment of randomness.
No, the below one. Yeah, yeah.
Okay, okay, this R, a vector of R. Okay. Here I'll give you some intuition. For example, we have A1, suppose the degree is only 3, okay. We have 4 coefficients for the fx. So then we generate same number randomness for the coefficients. So we plus them together. You kind of we can see, okay, R0 is protected A0, so we plus them together, R0 plus A0 to protect A0, right? So, because A0 is a secret, and then plus with a randomness, then the result will be randomness, right? But here's the thing. So if we just we plus them together, the prover can cheat verifier, right? So that's the reason why we should put A0 plus E times R0. E kind of is a separator. So even the result of this addition is random, random kind of. The verifier cannot get the A0. Sorry, use different R0 plus E times A0. So R is protected A0, but before the addition, the prover has to times E to make sure that okay, we added two values together, but still they are separated by a challenge number. To guarantee that there's no space for prover to cheat, to forge the proof. So 1A and 1R. So the randomness is kind of like a key to encrypt A.
Why would it be no space for the prover to cheat with E times A?
Okay. Okay. Just because we can prove that. We can prove that the prover cannot cheat by using a extractor algorithm to extract A0 out of box. So this was the sessions 1 week ago.
They're
So
all as a recording. If you really want to go for all the sessions, we have a recording.
yes. So we literally can prove that. We can prove that. We can prove if we do this way, it'll be fine. Yeah.
I'll check out the previous video.
Yeah. Okay. Okay. Okay, any question? So I remove this map. Okay, so bulletproof. It's a little bit complicated. Okay, for bulletproof, what we want to do in bulletproof is that we want to reduce the third step. The basic idea here as the third step, the prover to split and fold this vector instead of sending them into the verifier. So the prover asks the verifier additional. Sorry. I'm sorry that. There's some water. So.
I think it's.
Yeah. Thank you. Okay. To make sure that the prover can compress the third message. Okay, the idea is like this. Okay, I write the first step. Here's the thing. Here is some tricky part. So I put it here. But I don't want to go deeper about the. Okay, let me think. Okay. I'm coming with simpler. Okay, the basic idea is here. Okay. So the pulp input is like this. Okay, A equals to A0, A minus 1. And we use a vector like this. Okay. And okay. Okay, let me just simplify the protocol. Simplify the protocol. Okay, no, just okay. R E here. We got E here. Okay, as the third step. Okay, let me do the fourth step first. Got a mu0 from verifier. The prover will use mu0 to split and fold Z, right? We split Z into ZL vector and the ZR vector. So now introduce another notation, new notation. So saying that, okay, here give the notation here that A1, A2, A4, A3 equals to A0, A1 parallel A2, A3. Okay, it's a split. Okay, split the array into the lower part and the higher part. Okay, so prover split Z into half, and then use the mu0 to fold them together. we got a Z prime equals to ZL plus mu 0 times ZR. We'll just fold them together to make sure it's shorter. Right? It's only half size of Z vector here. But to make sure that the prover, there's no space for prover to cheat. So the prover has to commit something before split fold. Okay, this is called a split fold. Let me use this one. Split fold, a very important technique. Split and fold. Okay, split and fold. The smart trick here is that the prover also split fold this, the commitment, the base elements of the commitment, 0, 1. And the commit that, sorry. This we use A, B, C, D. Let me see, okay. CL equals to ZL, okay. GL and GR. Okay. The prover will send CL, CR. They're also commitments. But the commitment is kind of weird. Okay. We use the inner product notation to compute the commitment. So the point here is that, okay, this notation is still an inner product, right? The black box. So I frequently I often use the black box as a commitment. But the definition of commitment is actually another inner product. Except that for value vector and the value vector inner product, here the commitment is that the left component of the inner product is the value vector, and the second component of the inner product is a base element. It's the elliptic curve point. But still, to make sure that so bulletproof. The smart idea of bulletproof is that the authors found that we can we treat the commitment as the inner product too. So we can make the things something happen in a beautiful and a symmetric way to compress this message. So let me just write down the protocol, then we do some calculation and the reason, and then to say if this idea is correct. Okay, after 2 steps, what happened? The verifier can use RECLCR to compose. You know, they are just
The first two, yeah, first two rounds should be the
Like,
only one.
Prover should sing the
I-
first two arrows, first two arrows.
first what?
Arrow.
In the diagram,
Like from
the
prover,
values are being sent the wrong way.
Interact.
Yeah.
Interact. The first two.
First step, R and E should
Yeah.
be.
Sorry. Yes. Okay, just trying to simplify the protocol, okay? Good. Thank you. Now the verifier can construct the commitment of Z prime. Sorry, Z prime. Yes. So here the verifier, the prover can send the Z prime. The verifier can verify this this protocol by just commit, Z prime. Oh yeah, let me forget something. And also it do the split fold of G. The G prime equals to GL times mu0 to -1 times GR. And then because all the G elements are public inputs, so the verifier can also do this split and fold. So the verifier will same with prover split and fold. Split and fold. Split and fold what? Split and fold the G prime equals to GL plus mu0 times -1 GR. And then the verifier can verify G prime if it's equal to R plus E times A plus CL CL times mu0. I think, yeah, -1 times CR times mu0. Okay, here I should use R plus A. Okay. Okay. Okay, here this equation, this check is to check, is a proof of knowledge check. To check if a prover has knowledge of Z prime. Sorry. Knowledge of the folded A knowledge. Okay, but here, this new protocol compared to this one, we add two more interactions. So the prover has to commit 2 more group values, but at the last step, the prover only to send half size of the opening. Okay, z prime size is only half of z vector. So right now we successfully reduce the whole proof size into half. And then we can do more. So the prover doesn't have to open here. So prover can ask more challenge number to recursively cut into half. So actually here the prover can ask more, send another commitments and again another mu1, another. So here, C1 prime. Here the C1 CL prime equals to ZL prime plus GR prime. CR prime equals to ZR prime GL prime. Okay. And the prover has to do another spin fold. So here. So the split fold kind of split and the Z prime into ZL prime parallel ZR prime and G prime split GL prime parallel GR prime. And then the Z double prime equals to ZL prime plus mu0 times ZR. Okay. The G double prime matrix will fold of GL prime R plus mu1 to -1. The GR prime vector. Okay. Spin the fold again. Okay, spin the fold. And then verifier can construct that, okay, if right now, if okay, we are satisfied with the reduced size, then for us can send the opening. Consider the opening Z double prime. And the Z double prime set of is only 1/4 of this value. Okay. And the prover can instead check this puzzle. G if this is equal to question mark R A plus E times A plus CL CR CL prime CR prime at the mu0 and 1 plus mu0 mu1 plus 1. Okay. But if we don't satisfy with the proof set, okay, just like recursively do this kind of stuff, right? All the way to mu k then the verifier will check this ZK. Okay. The verifier can verify the protocol here. Okay, actually it's not a full bulletproof IPA. Because the verifier has to verify if the verification, the evaluation of this polynomial here. We will make that protocol even more complicated. Okay. Oh, it's almost 6. Is that 5? Is that 5 p.m. 5. Oh my god. Are you okay?
Yeah.
The final equation is not involved with mu k.
Yeah, we'll just ignore it. So I should have put all of it here. But before that, I should have added something into the protocol, make sure it looks like a real probability. Okay. I think we need 2 more. Sorry, 5 more minutes to add something to it. Okay, shall we stop here for a minute or let's continue?
Keep going.
Should let me make it more like real bulletproof. So here, the prover use this protocol can prove the prover knowledge of this one. But the difficult part of this protocol is that the prover split and fold the coefficients, right? We have to come up with a new way to split and fold the polynomial at the same time to make sure for each reduction, the verifier can also verify this folded polynomial evaluation equals to something. And from the verification, the verifier can make sure that all the way to the beginning of that, okay, I've evaluated that alpha equals y. So now we have to do a parallel split and fold. Using the same technique, but split and fold to calculate this inner product of z and and alpha. Okay, pretty. Probably can. This part. Okay. Let me write down the whole particle. Okay. It's not full spirit. Okay, write the whole particle. Prover and verifier. Okay. Okay, there's another technique that's very important, but I never talked before. Because using Piston comment, we can compose, or what I can say, to aggregate the multiple complement into one. So make the proof size even smaller. So let me write down the IPA for the bullet IPA here. That first of all, the prover has to send another, for example, lambda. Okay, lambda.
It's from the prover to the verifier.
So verifier to the prover.
Okay.
It's a very important step to make sure. So lambda is for, so what we want is that we want to aggregate, we combine the complement of A and the complement of the evaluation. So let me use another U from the group. So we choose another, okay, this U probably from the Piston complement, the base element. So we just pick one. Specific for commit the evaluation level. So the prover get a lambda from verifier, then prover will calculate U prime equals to lambda times U. Same. Verifier also calculate U prime. It's kind of a preparation for the following problem. And then, yes, it's, the RE stuff, and then the E. Then, so the CL and CR. But here CL has different value. We should add the evaluation part into CL. CL looks like this. Z. Actually, Z. ZL. GR plus ZL alpha vector, the higher part of alpha vector. So, okay, times U prime. Put it into box. Okay, this part will be a complement instead of value. Okay, this inner product of value and put it in box. Okay, because U prime is a proof element. And CR equals to ZR GL times ZR alpha vector lower part of alpha part. And then got the new 0, 1, 0. And then if we are calculate CL prime equals to the L prime GR prime vector plus the L prime alpha prime. So the prime means that it is a folded version of each vector. So for every vector, the prover will split and fold them into a smaller one. Okay. So the U prime is the R. So the prime vector. And then can CL prime CR prime, and then got another U1, and blah 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 to CLK CRK, and then got the mu K, then open the K the ZK plus 1. Okay. Suppose we split and fold, eventually we split we convert the whole vector. If the length of vector is power of 2, then we can fold them into just one value. Suppose that, okay, we successfully fold them into one value. So Z k minus 1 is not a vector. Yeah. Then the vector just simply verify using two equations. The first equation looks like Z k minus 1, because it's already the value of k minus 1. So k, so G to k minus 1, so k plus 1 generation of G is the folded group element from this G vector. So here the folded group element is we fold them, by logarithmic steps. We eventually got this one. This is equal to R plus E times A plus sigma I from 0 to K CL CL, yeah, 0 K I times U I is 1 plus CR I plus U I. Okay. And here the two checks has already. Okay, here we should put. Should add here plus y with u prime. Okay. Okay, anybody can verify. So I'm not sure. I'm not quite sure about this. Yeah, almost. Okay, I have to say this is not the realistic proof yet, because we remove the blinders all the way. So in realistic bulletproof IPA, we will, for each commitment, we should add more blinder here to protect every commitment won't leak any information to make that protocol perfect in their knowledge. But here is simplified, still a simplified version, but it's kind of almost the picture of the bulletproof. Okay, it's 5 p.m. I think the next session could be much easier.
Also, maybe we can start a bit earlier. I think today was the latest session to start, right?
Sorry? Earlier?
Like
Okay.
questions.
Okay. Okay. Thank you for coming.